A computer was given 138 stones and a simple task: put Peru's shattered wall back together. Each block had been photographed, measured, reduced to a clean outline, and entered into a system designed to search for matching edges. The researchers expected the machine to notice combinations that tired human eyes had missed. Instead, the reconstruction began to break apart. Possible matches appeared, then vanished when the angles were checked again. Shapes that seemed perfect from the front failed when depth was considered. The more the system calculated, the less certain the answer became, and that failure may be the most important discovery of all. These were not random stones lying in an empty field. They came from Cruz Moco, a partly dismantled sector of Sacsayhuaman, the enormous Inca complex overlooking Cusco in southern Peru. For centuries, visitors have stared at the famous zigzag walls and asked the same question. How did builders without iron tools, modern cranes, or wheel transport shape and place stones, weighing more than 100 tons? The newest digital work has pushed a different question to the surface. What if the walls we see today are not the complete mystery? What if they are only the surviving lower edge of a much larger design that was broken, scattered, reused, excavated, forgotten, and then misunderstood? That is where the story becomes uncomfortable. Modern technology was supposed to make the site easier to explain. LiDAR could map the ground, drones could photograph every slope, computer models could test wall movement during earthquakes, algorithms could compare stone shapes faster than any archaeologist. Yet when these tools were finally turned on Sacsayhuaman, they did not produce one clean answer. They revealed layers of missing information. They showed that old excavations had been lost in the landscape, that hidden water features had gone unrecognized, that occupation began before the imperial Inca phase, and that some walls praised as almost indestructible may be more vulnerable than their reputation suggests. So the new finding is not that a machine discovered aliens, melted stone, or a secret energy system. There is no reliable evidence for any of those claims. The finding is more serious because it is supported by measurements. We have been trying to explain Sacsayhuaman while looking at a damaged fraction of the original complex. We have treated isolated foundations as complete buildings, scattered stones as meaningless debris, and surviving walls as if they represent everything that once stood there. The new digital surveys are beginning to show how much was removed, how much was buried, and how much even modern archaeology misplaced after it was uncovered. Sacsayhuaman stands on a high ridge north of Cusco, roughly 3,700 meters above sea level. From the open ground below its terraces, the walls rise in 3 long zigzag lines. The largest blocks sit in the lowest courses, some taller than a person and broader than a small room. Their faces are rounded, but their edges turn in complex directions, meeting neighboring stones without mortar. A single block may touch several others. The joints do not follow neat horizontal rows. They climb, dip, turn, and lock together, creating a surface that looks less like ordinary brickwork and more like a frozen field of stone shapes. Spanish witnesses were stunned by it. Pedro Pizarro, who saw the complex in the 16th century, wrote about stones so closely fitted that even the point of a pin seemed unable to enter the joints. Other chroniclers described towers, rooms, storage areas, ceremonial spaces, and walls that appeared beyond human strength. Their wonder later became fuel for modern myths. But the witnesses also placed the complex firmly within Inca history. Peruvian cultural authorities state the construction began under Pachacuti, the ruler who transformed Cusco and expanded the Inca state, and continued under later rulers, including Topa Inca Yupanqui, Huayna Capac, and Huascar. That description matters because Sacsayhuaman was not simply a defensive wall. It was tied to the sacred and political center of Cusco and described as the house of the son of Hanan Cusco, the capital's upper division. The wider part contains shrines, carved rocks, channels, and foundations. Calling it a fortress is not completely wrong, but calling it only a fortress reduces a sacred imperial center to one episode of war. Then the destruction began. After the conquest, Sacsayhuaman became a quarry for colonial Cusco. Stones small enough to move were taken for churches, houses, and government buildings. Upper structures disappeared, carefully shaped blocks were dragged downhill and given new lives inside a city built over the Inca capital. The reason the lowest giant stones survived may not be mysterious at all. They were simply too large and too deeply seated to remove cheaply. What tourists admire today as the monument may therefore be the portion the dismantlers could not carry away, not the portion the Inca considered most important. This is why the latest work at Cruz Moco is so revealing. In a study published in 2026, a team examined 138 dispersed stones from an early construction area. They studied the facades manually and computationally, treating each stone as an independent unit and reducing its visible geometry to a two-dimensional silhouette. The goal was not to announce a magical final reconstruction. It was to test whether repeated shapes, aligned edges, and possible architectural roles could be identified in a systematic way. Human inspection produced some possible groupings. The computational matching did not deliver a dependable solution. At first, that sounds disappointing. The machine did not solve the wall, but consider why. A stone is not a flat puzzle piece. Its important contacts may curve backward, narrow inside the wall, or continue beneath soil. Weathering changes edges. Damage removes corners. A photograph can distort scale. Some blocks may no longer be standing in their original direction. Others may have belonged to separate buildings or different construction phases. Reduce all of that to a two-dimensional outline, and the system is forced to compare shadows of objects rather than the objects themselves. It can calculate similarity, but similarity is not proof that two stones once touched. The researchers were unusually open about these limits. Instead of hiding failed attempts, they reported them. That honesty is crucial because AI reanalyzed the walls can easily become a misleading headline. The actual lesson is not that artificial intelligence exposed a forbidden ancient technology. It is that computational tools are only as strong as the data and assumptions given to them. When the site is fragmented and the stones are three-dimensional, a flat matching system can create false confidence. The algorithm's failure became a warning. Before claiming a reconstruction, researchers need better spatial data, stronger records of depth, and careful archaeological context. Another digital investigation produced results that were far more direct. A drone-mounted LiDAR survey covered about 69 hectares of Sacsayhuaman. LiDAR sends laser pulses toward the ground and measures the time they take to return, creating a dense, three-dimensional cloud of points. When processed carefully, this can reveal small changes in elevation hidden by grass, erosion, and uneven terrain. The team compared those digital terrain models with old maps, aerial photographs, excavation reports, and oral histories. What emerged was not a lost city under the jungle. It was something stranger, the lost footprint of archaeology itself. More than 24 old or poorly documented excavation trenches were relocated with sub-meter accuracy. These were places where archaeologists had already disturbed the ground, sometimes many decades earlier, but whose exact positions had faded from reliable records. Think about the implication. Researchers were trying to understand an ancient site, while parts of the modern research history had become archaeological mysteries of their own. Without knowing where earlier trenches were located, a new team could mistake disturbed soil for an ancient feature, repeat an old excavation, or disconnect artifacts and dates from the architecture they were meant to explain. The LiDAR work did more than recover lost trenches. It helped place old radiocarbon dates, descriptions, and excavation results into a modern map. In the Cruz-Moco sector, it clarified sequences of occupation that began before the imperial Inca transformation of the ridge. It also identified previously unrecognized architectural and hydraulic features. That does not prove the famous megalithic walls were built by an unknown civilization. It shows that the hill had a longer and more complicated history than a simple story in which Pachacuti arrived at an untouched place and ordered one enormous project from the ground up. The dating layer matters more than it sounds. When the upper structures were dismantled, the workers did not carefully sort the rubble by phase. They took what was easiest to move. Foundation cuts from earlier occupations ended up mixed with broken fragments from later Inca construction. Without precise trench locations, the radiocarbon dates could not be tied to the right walls. With them, the team could begin to separate pre-imperial layers from the imperial transform. The sequence is not just academic. It changes who we say built each piece of the ridge. The hidden hydraulic features may prove especially important. Water in Inca architecture was rarely just a practical afterthought. Channels, fountains, drains, springs, and controlled flows could serve agriculture, protect foundations, organize space, and carry ritual meaning. On a ridge exposed to heavy seasonal rain, drainage was necessary for survival. Water entering behind a massive retaining wall can increase pressure, wash away supporting soil, and weaken a structure that appears solid from the front. A carefully planned network of channels could therefore be both engineering and ceremony, protecting the site while connecting it to ideas of fertility, purity, and sacred landscape. This is one reason the new digital map matters more than a dramatic claim about a single stone. A wall cannot be understood by measuring its visible face alone. Researchers need to know the slope behind it, the fill beneath it, the drains crossing it, the buildings that loaded it, and the paths that guided people around it. The living three-dimensional model now being developed by archaeologists and visualization specialists is designed to bring those layers together. Handheld LiDAR, drone photogrammetry, geographic information systems, architectural modeling, old descriptions, and surviving foundation widths can all be tested inside one changing digital space. The team calls some reconstructed upper volumes ghost forms. That name is appropriate because they are not presented as certain buildings returned from the dead. They are evidence-based possibilities rising above real foundations. If a footing is wide, it may support a taller wall than a narrow one. If several foundations align, they may define a room, passage, or platform. If a Spanish account describes towers in a certain area, the model can test whether the surviving base could carry them. Each guess remains adjustable. As new evidence appears, the digital structure can change without pretending that one beautiful image is the final truth. The emerging picture is enormous. The zigzag terraces may have formed only the front of a dense complex of towers, courtyards, rooms, storage spaces, roads, and sacred places. A person entering the original site would not have seen today's open ruin. Upper walls and buildings may have filled the view, turning the giant lower stones into the base of a carefully staged imperial landscape, designed to control movement, sight, ceremony, and the emotions of visitors. This vision is consistent with how Andean cities were composed in other places. Cusco below used large stone alignments to organize space, sightlines, and ceremonial flow. Ollantaytambo carried giant blocks uphill for ritual and political theater. Machu Picchu fit entire channels, plazas, and site corridors into a mountain setting. None of those places would be understood if we only saw the stones still standing in their lowest course. Sacsayhuaman almost certainly followed the same rule. The polygonal walls are the keystones of a much larger design that has been erased from sight, but not from the data. This brings us back to the stones. Digital mapping can reveal what is missing, but it cannot remove the physical challenge of what remains. Some blocks in the lowest walls are estimated to weigh well above 100 tons, with higher estimates approaching 200. The exact numbers vary because irregular stones are difficult to measure and density must be estimated. Even the lower estimates are extraordinary. The Inca had no oxen or horses before the Spanish arrival, and wheeled vehicles were not part of Andean transport. Moving such mass across sloping ground required preparation, ropes, ramps, levers, coordinated labor, and leadership capable of controlling danger. The logistics of moving a heavy block were not magic. They were a sequence of small problems solved in order. First, the path had to be cleared and leveled. Stumps and loose ground were removed. Second, the route had to be graded so that gravity helped rather than fought the workers. Earth ramps were built up, maintained, and sometimes dismantled after the block had passed. Third, the stone itself was brushed, patted, and rolled on wooden rollers and logs. The people who built walls in the Andes had plenty of experience with regular timber. Fourth, ropes were tied around the block in long loops so many workers could pull together without snapping the line. And fifth, the block was guided close to its final position, where the fine-fitting work began. The fine fitting was the hardest part. A giant block had to be moved near its final position, tested against neighboring surfaces, marked where contact was too high, pulled away or lifted enough for more material to be removed, and returned without killing the workers below. Builders may have used earthen ramps that allowed a stone to be raised gradually while walls grew around it. Clay, pigment, or dust could mark high points. Ropes made from strong plant fibers could be renewed and multiplied. Levers could shift loads over short distances. There is evidence for the tools used to shape Inca stone. Archaeologists have found hard hammerstones at quarries and construction areas, and unfinished blocks preserve stages of reduction. Builders could strike away large projections with heavy tools, then use smaller hammerstones for finer shaping and abrasion. Quarry studies show selection, rough cutting, finishing, and transport as parts of an organized sequence. The contact geometry at Sacsayhuaman is its own kind of evidence. Each polygonal block has many flat surfaces where it meets neighbors. Some contacts run vertically, some at a tilt, some slightly curved. Each meeting point is unique, but the rules across the wall are consistent. Faces meet in tight closure. Edges align across joints rather than stacking horizontally. Inward tilts keep blocks locked against their neighbors under gravity. The geometry does not need modern tools to explain, but it does need careful planning, repeated trial, and a workforce able to read the stone. This does not mean every detail is settled. The exact method used to transfer complex contact shapes between the largest blocks remains debated. Coring routes, ramp designs, and team sizes for the biggest lifts are all still open questions. But not knowing every step is not the same as humans could not have done it. The strongest mystery is not whether stone can be shaped with stone. It can. The real challenge is efficiency and control. The irregular joints, however, are not decorative. They serve structural ends that researchers have only begun to model. This may also explain why the stones were made so dramatic. The Inca did not choose the easiest possible wall. Smaller rectangular blocks would have been simpler to transport and replace. The giant polygonal style turned construction into a public statement. The state could take pieces of the mountain, move them, fit them, and make them stand as if the landscape itself had joined imperial order. In Andean thought, stone could carry identity, memory, and sacred force. A block was not merely dead building material. Its origin and placement could matter. Engineering and belief were not separate departments. They were parts of one act. The irregular joints also affect how the walls behave during earthquakes. Popular explanations often claim that Inca stones simply dance and fall back into place, making the structures nearly indestructible. The truth is more complicated. Dry masonry can move slightly without the brittle cracking seen in rigid mortar. Large blocks provide weight, multiple contacts, and inward-leaning faces can improve stability. Irregular joints may prevent long, straight cracks from running through the wall, yet survival does not mean immunity. Many upper structures are gone, and the walls we admire are the survivors of both earthquakes and deliberate dismantling. A 2024 engineering study modeled a section of the Sacsayhuaman Wall by treating each stone as a rigid body and calculating interactions between neighboring blocks. The researchers tested the model with signals and 3 Peruvian earthquake records. Their result did not support the simple legend of an invincible wall. Under certain shallow earthquake conditions, ground acceleration above about 0.2 g could cause significant damage and threaten stability. The model also highlighted residual movement, meaning stones may not return perfectly to their previous positions after shaking. A wall can survive and still slowly change. That finding is hard to ignore because it reverses the usual story. People often look at Sacsayhuaman and assume that the past solved earthquakes better than modern engineers. The model suggests something more realistic. The Inca created a strong system suited to a seismic landscape, but it still had limits. Its present condition may include small movements accumulated through centuries. Drainage failures, soil loss, visitor pressure, weathering, and future earthquakes could interact in ways the original builders never faced. Digital analysis is not only about explaining how the wall was built, it may become essential for keeping it standing. This is where artificial intelligence could become genuinely useful, though not in the sensational way many videos suggest. Machine learning can help classify point clouds, detect small changes between scans, identify cracks, compare block movement, and flag areas where vegetation or erosion may hide features. Future systems may search full 3-dimensional surfaces rather than flat silhouettes. They could calculate thousands of possible stone arrangements while rejecting combinations that violate gravity, wall thickness, quarry type, or archaeological sequence. The machine will still need human judgment because a mathematically possible match may be historically impossible. Suppose 2 stones fit perfectly in a model. If one came from a layer built a century later, they did not originally touch. Suppose an algorithm detects a straight line beneath the grass. It might be an ancient drain, an old excavation edge, a modern cable trench, or a natural break in the soil. Context decides the meaning. 2-dimensional matching fails because the wall itself is 3-dimensional. The Cruz Moco stone is not just a face to the camera. It has a back, sides, and interior contact surfaces that determine how it fits in a real wall. Some contact surfaces are concave, others convex. Some curve behind the block. Some meet neighbors under an angle the photograph cannot show. Reducing this to a flat outline throws away most of the geometry that matters. When the outline matches something else, the match may be real, or it may just be 2 stones that happen to look similar from the front. 3-dimensional scanning changes everything. A full mesh captures the stone's entire visible surface. Buried sides, if exposed during future conservation work, can be added. Surface damage can be mapped separately from original shaping. Rock type can help divide blocks by quarry and construction phase. Microscopic tool marks might reveal which surfaces were finished together. Soil records could estimate where stones were found before they were moved. Structural software could test whether a proposed arrangement carries weight safely. AI could then rank possibilities, not announce a single answer as fact. That is why the most exciting recent work combines technology with archives, field inspection, and local knowledge. LiDAR did not speak by itself. Researchers compared its patterns with maps, reports, photographs, and oral histories, then walked the ground to verify what the screen appeared to show. The danger comes when the computer's authority is used to hide uncertainty. An image labeled AI reconstruction can look final, even when it is based on missing walls, uncertain heights, and artistic choices. A colored heat map can appear scientific while depending on weak input. The Cruz Moco study is valuable because it demonstrates the opposite approach. The team allowed the algorithm to fail in public. They showed that reducing complex stones to 2 dimensions was not enough. In doing so, they provided a method other researchers can improve instead of a perfect picture that no one can challenge. The failure points toward the next breakthrough. Every one of the 138 stones could be captured as a detailed 3-dimensional mesh, including hidden sides where access is possible. Surface damage, mapped separately from original shaping, could keep the algorithm focused on real contact geometry. Rock type could sort the stones into quarries that the Inca might have used in shifts over decades. Microscopic tool marks could reveal which surfaces were finished together, a clue to workers and phases. Soil records from the dig could estimate where stones were found before they were moved. Structural software could test whether a proposed arrangement carries weight safely and matches the wall's restraint during an earthquake. There is another mystery hiding behind all of this. Why was Cruz Moco dismantled? And what did its original architecture do? Was it an early experiment in imperial construction? A ceremonial sector changed as Sacsayhuaman expanded? Or a place whose stones were later harvested for another project? The new geometric study suggests possible architectural roles, but refuses to claim a final reconstruction. The LiDAR work places the sector inside a longer occupation sequence and wider system of features. Together, they show a landscape repeatedly built, opened, altered, and remembered. The wall was not created in one frozen moment. That may be the most important correction to the popular image of the Inca. Their architecture is often presented as a lost trick that appeared fully formed and then vanished overnight. Real evidence shows development, variation, repair, reuse, unfinished work, and political change. Inca masons learned from older Andean traditions while creating styles that were distinctly their own. Different crews worked at different qualities. Some stones were left with bosses or rough surfaces. Some projects stopped before completion. Skill was extraordinary, but it was human skill carried by people, institutions, and traditions vulnerable to conquest and disruption. The newest data makes the Inca achievement more impressive, not less. It removes the lazy explanation that the stones must be impossible because we cannot instantly reproduce them. Instead, it reveals an entire system: quarry knowledge, organized labor, landscape planning, drainage, ritual purpose, seismic awareness, and construction choices that work together. It also restores the people who occupied the ridge before the imperial transformation and reminds us that Pachacuti's builders inherited a living place. The story becomes deeper than one genius architect or one secret tool. It becomes generations of human decisions written into earth and stone. The scans also create urgency. Sacsayhuaman is not finished revealing itself, and it is not guaranteed to survive unchanged while researchers study it. Earthquakes remain a threat in Cusco. Heavy rain can expose or damage buried features. Tourism brings attention and resources, but also pressure. Vegetation can protect soil in one place and hide instability in another. Old interventions may affect drainage. Every new survey becomes a time capsule, preserving the exact position of surfaces so future teams can detect movement measured in centimeters or even millimeters. The digital copy may warn when the physical wall begins to shift. This is the real power of reanalysis. It does not replace the monument. It gives the monument a memory more precise than any notebook. A future earthquake could move hundreds of blocks slightly. Without a detailed earlier model, those changes might be impossible to separate from ancient irregularity. With repeated scans, engineers can identify which stones rotated, where joints opened, and whether the slope behind the wall deformed. Algorithms can search billions of points for patterns no person could track manually. In that role, the machine is not exposing a forbidden past. It is helping prevent another part of the past from disappearing. So what did AI actually find in Peru's greatest walls? It found that the question was too simple. The wall is not one object with one secret. It is the surviving face of a vast, damaged complex. The first computational attempt to match dispersed stones showed how easily flat data can mislead. The LiDAR survey recovered more than 24 forgotten excavation trenches and revealed architectural and water management features hidden in subtle ground shapes. Digital reconstruction showed that foundations can support multiple possible upper forms. Engineering models showed that famous earthquake resistance has real strengths and real limits. Most of all, the new work exposed a gap between what the public sees and what the evidence allows. A photograph makes Sacsayhuaman look complete. It is not. A viral explanation makes its construction sound either fully solved or totally impossible. It is neither. Archaeologists understand many tools and processes, yet important details remain uncertain. The site belongs to Inca imperial history, yet the ridge contains earlier occupation. The walls survived centuries, yet they are not invulnerable. Computers can reveal patterns, yet they can also fail when the past has been flattened into incomplete data. And somewhere among those 138 scattered stones, there may still be a match waiting to be recognized. Not a supernatural code, but a real contact surface shaped by a mason centuries ago. Finding it could restore part of a doorway, terrace, stair, or sacred enclosure that has existed only as a broken outline. One correct connection could anchor several others. A wall could begin to rise digitally from the ground, not as fantasy, but as a tested possibility. Then the machine that failed on its first attempt would become useful precisely because researchers understood why it failed. For now, Sacsayhuaman keeps its deepest answer. The giant stones remain on the ridge, locked together beneath the thin air above Cusco. Around them, invisible lines from lost trenches, buried channels, vanished towers, reused blocks, and earlier settlements are slowly returning to the map. Technology has not made the place less mysterious. It has shown that we were asking a damaged monument to provide a complete story. The hardest finding to ignore is not that the Inca possessed impossible knowledge. It is that much of their knowledge may still be present, but scattered across a landscape we have only just learned how to read. And that leaves one final question. When future AI can compare every surface in full 3 dimensions, connect each block to its geological source, test every possible position, and place the result inside the newly mapped sequence of buildings and water systems, will it finally reconstruct the missing face of Sacsayhuaman? Or will the next model reveal that the Great Walls were only one visible part of an even larger design, forcing us to admit that the monument above Cusco was never simply a fortress, never simply a temple, and never simply a wall, but an entire engineered landscape whose true shape is still waiting beneath our feet?